Advanced Math, Lesson 17, Proofs of the Pythagorean Theorem, Proofs of Similarity. Now, we're not doing proofs this year, and we've already done proof of Pythagorean Theorem in our math lab, or if we haven't, we will do it soon. And that's a separate exercise in itself. So what we're actually going to take this lesson as time for is to review on these guys right here, these exponential fractions, because I know these give people trouble a lot. So I'll actually be going over lesson 17, number 24 and 25 right now. Starting with 24. Now when we come to these problems, it may not be as readily apparent what we're supposed to do, but you'll notice that we have two polynomials inside of parentheses, and even though they look very different, we have to use the FOIL method to solve them. So let's go to our work paper. Okay. Now, when we go to FOIL these, we'll just take first times the first. So 3x to the 1/2 times x to the 1/2. We get 3, and then we add the exponent. So 1/2 plus 1/2 is going to give us 1. So we get 3x. That's the first times the first. If we do outside times outside, 3x to the 1/2 times negative 2y to the 3/2. Negative 2 times 3 gives me minus 6 x to the power of 1/2, y to the power of 3/2. Then this inside y 3/2 x to the 1/2, that gives me plus x 1/2 y 3/2, and then we'll do last times the last, which we have negative 2y 3/2 times y 3/2. That gives me negative 2y, and then 3/2 plus 3/2 gives me 3. So 2y cubed. From here, all I have to do is combine like terms. So x to the 1/2, y 3/2, these are like terms. So what's negative 6 plus positive 1? We get negative 5. X to the 1/2, y to the 3/2. And that is our final answer. So this is as simple as it will get. We've combined all of our like terms, we've properly FOILed, and we've properly added our exponents. And again, we can write this polynomial in any order. We could have had the leading answer be negative 2y cubed plus 3x minus 5x. It doesn't matter the order, but what matters is each individual term and the sign in front of them are correct. Now, moving on to number 25. All right. So we've got some funny looking exponents here. So in this x, we've got an exponent that happens to be a polynomial. Down here, we have another exponent that happens to be a polynomial. Then we have some distribution of exponents here, and then here. This is a radical. It's a root, so it hasn't been turned into a fractional exponent yet. Very obviously, we're going to have to start off by rewriting our problem. We cannot let it stand as is. So I'll start with this cubed root of b to the power of 2y. Cubed root of b we can rewrite as b to the power of 1/3. All right, so we'll rewrite that as b to the power of 1/3. And then when we multiply by 2y, we distribute, we end up getting b to the 2/3 y. So b to the power of 2/3 y. And then we'll continue with this distribution, and we'll go with the denominator. We distribute this 1/2 here and here, so this can get rewritten as b to the 3/2 a to the 1/2, and then we're done with that. So we've successfully rewritten the right half of this fraction. Now the left half is just x's and polynomials being multiplied by these. So, well, wait, sorry, hold the phone. I copied this problem down wrong. So let's redo this section very quick. This isn't b to the 3rd power times a. It's actually supposed to be b to the power of 3a. So this is wrong. So we have b to the power of 3a times the 1/2, which gives us b to the 3/2 a power. So that's the correct value down here. Now, back where I was, the x's, these polynomial exponents. The way we're going to simplify this is we're just going to bring everything up to the numerator. And when we bring this exponent to the numerator, we have to distribute the negative to the whole polynomial. So when we bring this up, it doesn't just become negative 4a, it becomes negative 4a positive 1. So take this, we move it to the top, and we get x to the power of negative 4a plus positive 1. And we'll write that next to x to the power of 3a plus 2. Over here we then have b to the power of 2/3 y, and then this goes up to the negative, and then we have b to the power of negative 3/2 a. Alright, now we can combine these because this is all multiplication. They're all being multiplied, so we combine them by just adding the exponents. Now when it comes to adding these x's, we have like terms. Negative 4a plus 3a are like terms, so when we combine those, we just get x to the power of negative a. Then 1 and 2 add up to 3, so we could just write this as x to the power of 3 minus a. All right, or we can put negative a plus 3. I'm just going to write it as 3 minus a. I like putting those rational numbers up front. So the x's are complete. And then I go to the b's. How do I add 2/3 y and negative 3/2 a? Well, I need to get a common denominator. It's that simple. So we'll rewrite these as fractions, these exponents, and we'll put 2y over 3 minus 3a over 2. Okay, and originally these fractions would have been 2/3 y. All I'm doing is I'm taking this whole number y, putting it over 1, multiplying it to make it 2y over 3. Same thing with the a. Now we can see here that our common denominator to add these fractions is going to be 6, so I multiply by a value of 1, multiply by a value of 1. This becomes 4y, this one becomes minus 9a, and we can write them all over the common denominator of 6. So what I'm doing is once these become both written over 6, I just write them as one single fraction, and that's what we're going to do for our b. So these combine to become this, which becomes our exponent for b. We have b to the power of 4y minus 9a all over 6. And that's our final answer. All right. If you guys have any questions on every homework, feel free to send me a message on Moodle. And hopefully this is clearing up some of those fractional exponent problems that we're having. So I'm using these proof lessons as a nice break to review some stuff that we've been having trouble on, or to go over more new concepts.